Welcome to my CCSP Exam Cram series. We'll call it the 2023 edition, and in this installment, covering every topic in the official exam syllabus for Domain 1 of the CCSP exam, as well as my recommended exam preparation strategy incorporating proven learning techniques to take you further faster in preparing for exam day. So as a cybersecurity strategist and a VCSO for a regional bank, I can promise you the knowledge you gain in preparing for the CCSP exam will serve you well every day of your cybersecurity career. Perhaps more importantly, last year alone I helped hundreds of thousands achieve cybersecurity certifications like Security Plus, the CISSP, and now the CCSP, all without expensive boot camps. So in this series, we'll have 6 installments. That's one course for every domain of the CCSP exam. And when the series wraps up, I'll produce and publish a consolidated full course video. In Domain 1, we're focused on cloud concepts, architecture, and design. You'll notice the domain weightings are fairly similar, so we're going to give equal focus to all 6 domains throughout this series. To get the most from your exam preparation time, I recommend you pair my video series with the CCSP Exam Study Guide and Practice Test Bundle because it includes 1,000 flashcards, 1,000 practice questions, and 2 practice exams. They're available to you online at no additional charge. You can get the bundle on Amazon.com, and in fact, I've included a link to the latest exam bundle published in November 2022 in the video description. Because it's frequently requested, I've included a PDF copy of these presentation materials in the video description so you can download and review at your leisure as you prepare for exam day. And I've also included a clickable table of contents in the video description so you can jump forward and back throughout this video and indeed throughout the series as you prepare for the exam. So let's talk a moment about the exam itself. So the last update to the CCSP was in 2022 on August 1st. The new version was released. It includes now 150 questions, up from 125. That includes 50 unscored pretest questions, which in the words of ISC2 are included to help protect the security and integrity of the exam. They're really protecting against question dumps, sometimes called brain dumps, which are against the NDA of the exam, and truth be told, very unnecessary anyway. This is a multiple choice exam. It's 4 hours in length. It used to be 3 hours when ISC2 added the extra questions. They added an hour to the allotted time. Now, in terms of experience, candidates must have a minimum of 5 years cumulative paid work experience in information technology, as well as 3 years in information security and 1 year or more in one of the 6 domains of the CCSP common body of knowledge. However, there's a nice surprise. If you earn ISC2's CISSP credential, that can be substituted for the entire CCSP experience requirement. CISSP comes with its own 5-year experience requirement, albeit less specific than the CCSP, but you can just wipe that off the map by taking the CISSP exam, and I have a link to my free CISSP Exam Cram course. That's a very popular cert with employers and a great exam to focus on when you're 3 to 5 years into your cyber career. Passing score for the CCSP, 700 of 1,000 possible points. And there is no award for longest study time, so I recommend you make the most of your time and you knock this exam out in the least amount of time you need to master this material. So I'd like to talk for just a moment about my recommended exam preparation strategy. I have a number of techniques here that have a lot of science behind them to help you get further, faster in your exam prep. I want to start by talking about the power of repetition. In particular, I want to talk about a technique called spaced repetition. So every time you study a piece of material, over time you're going to forget part of what you've learned. We call that the forgetting curve. But what you'll find through repetition is that with each repeating session, you're going to remember a bit more for a bit longer. So in other words, the forgetting curve becomes a bit longer and a bit shallower with repetition. So how much time does it take to remember anything for the long term anyway? So to memorize material quickly, you'll need to go through that process of spaced repetition in shorter cycles, repeating right after learning and then a few minutes to a few hours apart. This is great if you're trying to remember content for the short term. You're doing it all within potentially even a couple of days. And this can be effective if there are just rough spots that you have that you can't quite commit to memory just before exam day. Now, to remember concepts for a long time, we need to space those repetitions, those repeating sessions out from a few minutes to a few hours to a few minutes, and then days, weeks, and even months potentially. So you can see the process is parallel, but the space between the repetitions makes a difference in how long we commit that information to memory. And that actually explains why those 5-day, $3,000 boot camps are actually so effective in getting you through exam day. They cram a lot of material in there, you repeat it quite a few times, and you remember it long enough to get through that exam. Many of us were labeled as a specific type of learner as children, perhaps a visual learner, or an auditory learner, or even a tactile learner. Since that time, research has actually shown that everyone benefits from a variety of sources. So I recommend you mix and match the techniques you like best as you prepare for the exam. That might include targeted reading from the official study guide, practice exams, live quiz or flashcard review, perhaps with a partner, PowerPoint review. You can review the PDF that comes with this course, and video content like this course tends to be my anchor. I like to use video learning and then mix in other techniques to fill in my rough spots, but mix, match, and repeat based on your preferences. Now, there's a question I get a lot, and that is, what do I mean by targeted reading? Well, I'll tell you. I mean, use the official study guide for topics you are struggling with, but not as a book you will read cover to cover. Use it when and where you need it to make the most of your time. Very unlikely cover to cover in the official study guide is going to be your best approach. And it's also been shown that understanding concepts before you attempt to memorize greatly improves retention because you understand what it is you're trying to memorize. It's not simply memorizing words. All right, so let's get down to business in Domain 1, Cloud Concepts, Architecture, and Design. Again, I will cover every topic mentioned in the exam syllabus, and I'm also going to incorporate examples of concepts using different cloud providers when possible to supplement your knowledge in areas where you may not have exposure to a cloud service provider yet. The CCSP exam is what we'd call vendor agnostic. It doesn't focus on a specific vendor like AWS or Microsoft Azure, but you'll find that the examples I provide give you context to help you more effectively remember the concepts. So I'd like to talk for a moment about what the official study guide calls exam essentials. Critical exam topics that, according to the guide, are very important to remember for the exam. Not the only topics, but definitely amongst the most important. For Domain 1, they call out the different roles in cloud computing, like service providers, service partners, access service brokers. Identifying the key characteristics of cloud computing, like on-demand self-service, multi-tenancy, elasticity, and scalability. Explaining the 3 cloud service categories, IaaS, PaaS, and SaaS, and the differences between them. Describing the 5 cloud deployment models, public, private, hybrid, community, and multi-cloud. Identifying important related technologies. And you see a lot of cutting-edge modern tech here, machine learning, AI, DevSecOps, quantum. We're going to touch on all of them. And finally, shared considerations in the cloud. Interoperability, portability, privacy, resiliency. We'll touch on them all, and I'm going to give you a tour of the shared responsibility model for cloud, which will provide a foundation that makes onboarding all the concepts related to this exam much easier. So let's get into 1.1, which is understanding cloud computing concepts. We have cloud computing definitions, so literally the definition of cloud computing according to NIST. cloud computing roles and responsibilities. You're going to hear some roles here you've probably heard of, like cloud service provider, and others maybe you haven't. We'll touch on key cloud computing characteristics. What are the promises of the cloud? Concepts like on-demand self-service, broad network access, multi-tenancy, elasticity and scalability, and just as importantly, what's the difference between those two? And we'll finish out 1.1 with building block technologies, diving into virtualization, storage, networking, databases, and orchestration, again with examples from your various cloud service providers wherever I can give them to you. First up is NIST Special Publication 800-145, which is the NIST definition of cloud computing. This is a model for enabling universal, convenient, on-demand network access to a shared pool of configurable computing resources that might include networks, servers, storage, apps, and services. It depends on the cloud category and the specific service we're working with, that can be rapidly provisioned and released with minimal management effort or service provider interaction. And that's the promise of the cloud, that resource consumption for the customer is easier while the cloud service provider handles the care and feeding of the underlying cloud infrastructure. And now on to cloud computing roles. We'll begin with cloud service provider. That's the company that provides the cloud-based platform, the cloud infrastructure, and applications to other organizations, to customers, as a service. Examples here: Amazon's AWS, Microsoft Azure, Google Cloud Platform. Those are the big three. If you see the CSP acronym in a question, they're talking about the cloud service provider, not to be confused with cloud services partner. A cloud services partner is a company that helps organizations to obtain and deploy cloud services. They may offer consulting services, they may offer software that runs in the cloud, or both. On the services side, Avanade, Tata, Accenture, all good examples of big cloud services partners. Next, we have the customer. That's the business or individual consuming the cloud services from the CSP. They're often using public cloud to complement or augment existing on-premises compute, resulting in a hybrid cloud configuration, currently the most common cloud implementation. And then we have the cloud service auditor. This is a third party that can conduct an independent assessment of cloud services, information systems operations, performance, security around the cloud implementation. Truly, the audit scope may vary. The key here is an independent assessment. That means the auditor is external to the customer or CSP organizations. Then we have the cloud broker. This is an entity that manages the use, performance, and delivery of cloud services. So more directly, they often negotiate relationships between cloud service providers and cloud service consumers, so between the CSP and the customer. They serve as an intermediary, an advisor, a negotiator between customer and CSP. So let's go a level deeper on the functions of a cloud broker. So they may serve in the area of service intermediation, so enhancing a given service by improving specific capabilities and providing value-added services to the cloud consumer, to the customer. They may help with service aggregation. This is where we combine and integrate multiple services into one or more new services. And then service arbitrage, which means the broker has the flexibility to choose services from multiple agencies, potentially resulting in a multi-cloud architecture. Now let's take a look at a few other cloud computing roles. These are less likely to appear on the exam, but just in case, worth knowing before you walk into the exam room. There's the cloud administrator, responsible for implementation, monitoring, and maintenance of the cloud, not unlike a systems administrator on-prem. Cloud application architect, the person who's adapting, porting, and deploying the applications. Let's talk about that word porting for a moment. So porting an application means moving that application, its associated services and databases, from an on-premises environment to the cloud. That may include some refactoring to prepare that application for operation in the cloud. Then we have the cloud architect who designs and develops solutions, so not unlike an architect on premises. The cloud operator, responsible for daily operational tasks. The cloud data architect, who manages data storage and data flow within as well as to and from the cloud. So you may notice a pattern here that some of these roles, while they have the word cloud in them, definitely look parallel to roles that we've seen in IT on premises. We have the cloud service manager, responsible for business agreement and pricing for the cloud customer, so maybe working as an employee within the customer, negotiating contracts with the CSP or partners. We have cloud storage administrator, managing storage volume and repository assignment, configuration, and potentially security. The cloud service business manager, overseeing business and billing administration. So this is the person doing the paperwork with regards to paying that bill, that operational expenditure. And then cloud service operations manager, who prepares systems, operations, and support for the cloud and administers services. And the further we went down this list, the more niche I'd say these roles are. You're not going to see all of these roles in any organizations, and most of them certainly only in the larger organizations. So finishing out cloud computing roles, one more less likely to appear on the exam, but important to mention, the Managed Security Service Provider, or MSSP, which is a company that maintains the security environment for companies running in the cloud. They may manage firewalls, IDPS, your SIEM solutions, and other security services and infrastructure. And they may even provide an outsourced security operations center that's staffed to monitor security operations and provide incident response. Now we're going to take a look at key cloud computing characteristics, those characteristics common in cloud platforms and services. There's on-demand self-service, where customers can scale their compute and storage needs with little or no intervention or prior communication from the provider, from the CSP. They can use what they want when they want. And their technologists can access cloud resources almost immediately when they need to do their jobs, providing agility in service delivery. They're going to be more responsive. And broad network access. Services are consistently accessible over the network, regardless of the user's physical location. And it's no accident for this reason that your big CSPs all have a global presence across not only every major continent, but across the busiest countries and regions within those countries. So close points of presence. We have multi-tenancy, which means many different customers share use of the same computing resources. Physical servers that support our workloads might be the same physical servers supporting other customers' workloads. And the underlying cloud infrastructure, the compute, the storage, the networking, it's all shared, and shared generally by multiple customers. You should also be familiar with the concept of oversubscription. Cloud providers are going to oversubscribe their total capacity, which means they'll sell more capacity than they actually have. So why would they do that? Well, because in the big picture, customers won't collectively be using all of that capacity simultaneously. And this is true in IaaS, PaaS, and SaaS scenarios, all three. Now, the level of cloud service provider responsibility will vary in those IaaS, PaaS, and SaaS scenarios. We'll talk about that in the shared responsibility model later in this video. We have rapid elasticity and scalability. This allows the customer to grow or shrink the IT footprint as necessary to meet their compute needs, their storage needs, without excess capacity. These two are related, but they're unique. So let's talk about the difference between elasticity and scalability. Elasticity is the ability of a system to automatically grow and shrink based on app demand. Capabilities can basically be rapidly provisioned and deprovisioned. Think auto scale, scaling out and scaling in, adding additional instances quickly, auto deploying these instances. They are ephemeral instances, available only for the time they are needed. Scalability, on the other hand, is the ability of a system to handle growth of users or work, the ability to grow as demand increases. The scalability is generally controlled by a SKU or service tier selection or the number of instances you're deploying. Scalability is more about deploying the necessary capacity for steady state operations day to day. Elasticity is adding that burst capability when we have sudden increases in traffic. Then there is resource pooling. This enables the cloud provider, the CSP, to apportion resources as needed across multiple customers, so resources are not underutilized and they're also not overutilized or overtaxed. This enables the provider to make capital investments that greatly exceed what any single customer could provide on their own using their own budget in their own data center. And it allows the provider, the CSP, to meet demands from multiple customers while remaining financially viable, while remaining profitable. One of the downsides here is this can result in some degree of location dependence that's beyond the customer's control. However, most of your major CSPs, and I'm talking about AWS, Azure, and Google Cloud Platform off the top of my head, do generally provide flexible options enabling customers to choose location even in their SaaS offerings. And the ability for a customer to choose location can be very important in data residency compliance. So if our data needs to reside in a particular country, as would be true in Germany and potentially in the EU with GDPR, that flexibility to choose where data resides in particular is one that is top of mind. And rounding out cloud computing characteristics, let's talk about measured service, which means that almost everything you do in the cloud is metered. It's measured and tracked for management and billing. And your cloud providers will measure metrics of resource consumption. They'll be looking at the number of minutes a virtual server is running. They'll look at the amount of disk space you consume. They'll look at the number of function calls you make in a serverless scenario, and potentially the amount of network egress and ingress. Generally with cloud service providers, network ingress, so getting data into the cloud, is free, but when you try to take it out, you're often going to pay for that. It's a tough metric to predict, so you do want to be careful in looking at how a service is billed. And measured service is also known as metered service. So whether you see measured service or metered service on the exam, two phrases for the same concept. Finishing up section 1.1, we're going to talk about the 5 building block technologies of the cloud, which are compute, network, storage, databases, and orchestration. So let's begin with compute. And in the area of compute, infrastructure as a service, or IaaS, is the basis for compute capacity in the cloud. The CSP provides the server, the storage, and the networking hardware, and virtualization of all of these components. The customer installs middleware and applications on virtual machines, and the customer only pays for what they use. The charges stop when the instance is stopped or deleted. We're going to dig into the boundaries of responsibility a bit later in this video in the shared responsibility model. Again, something not mentioned in the official study guide, but you're going to appreciate the context it brings to everything we're learning in this series. Let's talk about the basics of network. So cloud networking in the cloud is all virtualized to allow customers to design and customize the network to their needs. This enables customers to segment networks and restrict access however they'd like, implementing preferably a zero-trust network architecture. And physical network components are virtualized into a software-defined network, or SDN. Examples in major CSPs include VNet in Azure and VPC in AWS and Google Cloud Platform. So let's talk about an SDN. This is a network architecture approach that enables the network to be intelligently and centrally controlled or programmed using software. And SDN is defined by 3 separate planes, or layers, if you will. There's the management plane, the business applications that manage the underlying control plane and are exposed with northbound interfaces. I'll visualize a northbound and southbound interface for you in a moment. We have the control plane, which is where control of network functionality and programmability is made directly to the devices through the southbound interface. OpenFlow is the original protocol at the control plane and is still common today. And then we have the data plane, and the network switches and routers located at this plane are associated with the underlying network infrastructure. Now, data forwarding happens here, so this is also sometimes referred to as the forwarding plane. So just to visualize for you here, we have the control plane, the SDN controller, and the management plane, which is exposed to the control plane through the northbound interface, and the data plane, where our switches, and routers, our underlying network infrastructure resides. So again, management plane exposed through the northbound interface, data plane exposed to that controller through the southbound interface. And to dig in just a bit further here, the northbound interface ensures only trusted, authorized applications access critical network resources, and OpenFlow as a protocol at the control plane interfaces with devices through the southbound interface. Let's move on to storage. And storage varies by model, so whether we're talking about infrastructure as a service, platform as a service, or software as a service, your storage is virtualized as you'd expect. And the CCSP exam considers three types of storage: long-term, ephemeral, and raw. So ephemeral is relevant for IaaS instances, and it exists only as long as the instance, the VM, is up. That would be a temp disk generally. And raw storage maps to a LUN, to a logical unit number on a storage area network attached to a VM. So that concept pops up more in a hybrid scenario where we're dealing with a SAN directly on-prem. You're not going to see much around SAN in a cloud portal itself. It's all really virtualized. Now, long-term storage offered by some CSPs is tailored to the needs of data archiving. That may include features like search, immutability, and data lifecycle management. And long-term storage typically uses either volume or object storage infrastructure. So let's talk about each of those. So an example of a volume or block storage would be Amazon EBS and Azure Disk Storage. An example of object storage would include Amazon S3 and Azure Blob Storage. So let's talk about storage in the context of platform as a service. Here the focus is on databases, usually multi-tenant relational SQL database as a service. It might be Microsoft SQL, it could be MySQL, it could be PostgreSQL. And then there's big data as a service. These are non-relational or NoSQL data repositories like document, graph, column, or key value stores. Examples here include MongoDB, Cassandra, and HBase. You should also be familiar with the concept of storage consistency, which describes the time it takes for all data copies to be the same. We have strict consistency at one end of the scale that ensures all copies of the data have been duplicated amongst all relevant copies before finalizing the transaction to increase availability. And then there's, at the other end of the scale, eventual consistency, where data consistency is relaxed and it reduces the number of replicas that must be accessed during read and write operations before the transaction is finalized. Data changes in this case are eventually transferred to all data copies via asynchronous propagation over the network. And depending on the NoSQL flavor you're working with, some cloud services will offer you degrees of consistency. So you'll have options somewhere between strict and eventual to set the level of consistency that works in your application's model. So let's talk about storage in the software as a service or SaaS context. So we have content or file storage. So this is file-based content stored within the application. Microsoft Office is the perfect example. A content delivery network is where content is stored in object storage and then replicated to multiple geographically distributed nodes to improve internet consumption speed. What that does is places content near the points of presence where customers will access a service. There's information storage and management, so data entered into the system via the web interface and stored within the SaaS application. This often utilizes databases, which are in turn installed on object or volume storage. And when we think about software as a service, that's really just a service we use and don't think too much about the underlying infrastructure, so we'll talk about the boundaries of responsibility there in the shared responsibility model later in this video. So let's move on to databases. So multiple options are available. You have multiple flavors of relational and non-relational that we touched on a moment ago, but there are managed database services, so PaaS options that shift infrastructure maintenance to the cloud service provider. There are also IaaS hosted databases that are an option where PaaS is not possible or practical. So you have examples on the PaaS side of Azure DB for Microsoft SQL. They also have a MySQL flavor, a Postgres flavor. On the Amazon side, you see Amazon RDS and DynamoDB. And generally, PaaS is preferable, but we see the IaaS database options pop up where customers have isolation or compliance requirements that make PaaS just not practical at all. So let's talk about orchestration, the fifth building block. So cloud orchestration creates automated workflows for managing cloud environments, and they're building on the foundation of infrastructure as code, reducing manual administration tasks. And orchestration may be a script, a function, a runbook, or developed in an external workflow engine. So a few examples here: you have Azure Automation, AWS Systems Manager, or you could even look at third parties like Zapier that integrate with hundreds of services and multiple cloud platforms. We're going to close out section 1.1 with a look at some virtualization concepts you may see on the exam. So virtual assets can include virtual machines, which we talked about previously. Virtual machines can factor in a virtual desktop infrastructure or VDI solution, a managed desktop if you will. Software-defined networks and virtual storage area networks. So these are all virtualization concepts. And hypervisors are the primary components that manage virtual assets, but also provide attackers with an additional target. So both hypervisors and the VMs that run on them need to be patched and secured. So we have our compute, our network, and our storage. Let's talk about security issues with cloud-based assets. So storing data in the cloud increases our risks. So steps may be necessary to protect that data depending on the value of that data. We need to focus on our valuable assets. When we're leasing cloud-based services, you should know who is responsible for the maintenance and the security. And depending on the category we're working with, IaaS, PaaS, or SaaS, the level of responsibility of customer versus cloud service provider will vary. We're going to touch on these and break them down in the shared responsibility model shortly. The cloud service provider provides the least amount of maintenance and security in the IaaS model. So let's talk about hypervisors. We have the Type 1 or bare metal hypervisor that's installed directly on to the server hardware. Flavors there include VMware ESXi, KVM, and Microsoft Hyper-V. And then we have the Type 2 or hosted hypervisor, which is installed on top of a host OS like Windows or Linux. Varieties here include VMware Workstation and Oracle VirtualBox, to name a couple. So let's look at the characteristics of the Type 1 hypervisor to start. So it certainly has a reduced attack surface when we compare it to the Type 2 hypervisor that has a host operating system. And this makes the Type 1 hypervisor more secure if implemented properly. We see Type 1 hypervisors typically implemented for QA, load testing, and production scenarios, and the Type 1 hypervisor is typically more expensive than a Type 2 hypervisor. Now switching gears to the Type 2 hypervisor, the characteristics here vary just a bit. We have the increased attack surface due to the host operating system, and this makes it slightly less secure versus Type 1 even if implemented properly. It's commonly used for individual development and lab scenarios, and it's typically less expensive than a Type 1 hypervisor. That brings us to section 1.2, describe cloud reference architecture. So here we'll touch on cloud computing activities, cloud service capabilities, cloud service categories. This is where we touch on IaaS, PaaS, and SaaS. We'll talk about cloud deployment models, including public, private, hybrid, community, and multi-cloud. We'll talk about the shared considerations of cloud. But just ahead of cloud deployment models, I'm going to slip in a quick talk on the shared responsibility model, which is really going to ease your onboarding of most of these concepts. Then we'll touch on the impact of related technologies, everything from data science and machine learning and AI to containers, quantum, and DevSecOps. Let's start with cloud computing activities, and we'll begin by looking at activities according to ISO 17789 Cloud Reference Architecture and which parties map to which activity. So according to ISO 17789, the following are the responsibilities of the customer. So certainly using cloud services, performing any service trials to ensure the appropriateness of a specific cloud service, monitoring, administration, billing and usage reports. Certainly the cloud platform, the CSP, will provide billing and usage tooling often, but billing and usage reporting falls to the customer. And also operations, handling problem reports, performing business administration, administering cloud tenants, selecting and purchasing services, and requesting audit reports. These are all, again, customer responsibilities. Now, according to ISO 17789, these are the responsibilities of the cloud service provider, the CSP. Preparing systems, providing the services, managing assets and inventory, providing audit data, whether contractual or required by law, managing customer relationships, handling customer requests, performing peering with other cloud service providers, ensuring compliance, at least where compliance is mandated by law or the CSP promises compliance with regulations such as GDPR or FedRAMP or HIPAA, and providing, of course, network connectivity. And again, that's the CSP responsibility. Now let's look at the third party here, the partner. So partner responsibilities, according to ISO 17789, include design, creation, and maintenance of service. So that would be typical in an architecture scenario where the partner is providing consulting services. Testing, potentially performing audits as an independent assessor. Setting up legal agreements, assessing customers, assessing the marketplace, so really determining where the partner can effectively provide services that are value add in the cloud scenario. So just as a quick refresher on partner versus provider. So we have the CSP that delivers the cloud platform and infrastructure that customers subscribe to and use. And then we have the partner that provides the guidance and implements services and potentially software. So Microsoft, Amazon, and Google are providers, and partners are the service and software companies. We talked about some of these like Accenture, Tata, Avanade. And again, anywhere you see the CSP acronym, that is absolutely referring to the cloud service provider. Next on the agenda are cloud service capabilities, the capabilities, advantages, and efficiencies of the public cloud. So first we have application capability types, where we see an overall reduction in cost, reduced application and software licensing, reduced support cost, and a reduction in the need to worry about our back-end systems and those capabilities. Our cloud service provider gives us the ability as a customer to focus on business use cases while they handle the care and feeding of the underlying platform and infrastructure that previously would have been in our data center. Then platform capability types, language and framework support, support for multiple environments, and allowing customer choice and reducing vendor lock-in, as well as improving a customer's ability to auto-scale, giving us that ability to scale in and out as demand necessitates. And then infrastructure capability types. Again, scale, converged network, shared capacity. Remember, the cloud service provider oversubscribes, so they give us the appearance of infinite capacity. Self-service, on-demand capacity, high reliability, service resilience through distribution across regions. And where this is a capital expense on premises, it's an operational expense in the cloud. So as organizations move to the cloud, we see a shift in budget from CapEx to OpEx. And remember, the customer only pays for what they use. So let's talk about cloud models and services. In particular, I want to talk about the shared responsibility model as it applies to IaaS, PaaS, and SaaS. And this will help to differentiate the responsibility of the CSP versus the customer in your mind as we go through different scenarios. So when we're on premises, responsibility is easy. It belongs 100% to the customer. The customer is responsible for resiliency, availability, redundancy, all the way down to the wire. 100% yours. As we move into the cloud, in the IaaS model, infrastructure as a service, we see the cloud service provider takes on care and feeding of our virtualization infrastructure, the servers, the storage, the networking, and the hypervisor. We're really just consuming virtual machines running on top of the hypervisor. When we move into PaaS, we see the cloud service provider taking on more responsibility, now managing the OS, middleware, and runtime. And as a customer, we're really just responsible for our applications and our data. And when we move into SaaS, thinking services like Office 365, you see the cloud service provider, the CSP, takes on even more responsibility. And now we have a shared responsibility there for data and application configuration, but largely we're just using the service. So you see, as we move from IaaS into PaaS and SaaS, the CSP is progressively onboarding more and more responsibility, allowing us to focus as a customer on simply using the service. So just to name the advantages here, the CSP provides the building blocks, network, storage, and compute in the IaaS scenario. The CSP manages the staff, the hardware, the data center, and that gives us some key benefits here. Usage is metered, so we're paying for what we use. It eases our scale up, our scale out, our scale down. It reduces our energy and cooling costs in the data center because we're shifting our data center to the CSP's data center, right? Examples here include Azure Virtual Machines, Amazon EC2, and Google Cloud Platform's compute engine. So moving into PaaS, here we saw the customer is responsible for deployment and management of apps, and the CSP manages provisioning, configuration, hardware, and the operating system. They're taking on more responsibility for us. Key benefits in PaaS is that the core infrastructure is updated by the provider. It's really entirely off our plate. Global collaboration for app development and running multiple languages seamlessly. So in the PaaS construct, if we're hosting web apps or functions, we're going to have a good idea of the language support that comes from those CSPs, but they're generally going to support a variety of languages. Examples of PaaS services on the Microsoft platform would be Azure SQL, their API management function, Azure App Service. So all PaaS services where we're really just focused on the application and our data. Then finally, in the SaaS bucket, again, we're just configuring features as a customer. The CSP is responsible for management, operation, and service availability. And SaaS brings even more advantages here. The customer still has some responsibility in terms of access management and data recovery. For example, in Office 365, we typically have backups of that data, so if we have a ransomware attack, we can recover more quickly. Certainly in many of these SaaS scenarios, we'd be able to recover with the built-in capabilities of the SaaS service, but the customer can step in and add some recoverability of their own. Key advantages here, key benefits would include limited administration responsibility and really limited skills required. The bar for entry is very low when it comes to SaaS. You're just a consumer as a customer, and the service is always up to date. We're never worrying about the care and feeding, the patch management. It's all handled for us. And again, we have global access here, so available across continents, countries, and regions. Examples of SaaS services: Office 365, ServiceNow, Salesforce, all well-known SaaS applications. I want to talk about just one bit of nuance in the PaaS, in the platform as a service bucket, and that's really how is serverless, when we see that term serverless, how is serverless different from platform as a service in terms of customer responsibility? So we have PaaS on one hand, serverless on the other, and they do have some commonalities. In both cases, devs have to write code, and there is no server management. So we're really focused on our application and deploying that app. Now, there are some differences, though, between PaaS and serverless. So, for example, in PaaS, we have more control over the deployment environment. If I think about hosting web applications in PaaS, we can typically pick service tiers that give us some control over scale and isolation and some of our features. On the serverless side, we have less control over the deployment environment. Now, on the PaaS side, the application has to be configured to auto-scale. We typically have to configure the scale in, scale out through whatever mechanisms the PaaS service offers. Serverless generally scales automatically. On the PaaS side, the application typically takes a while to spin up. If you have a web app that hasn't been accessed in a few hours, the threads are going to die. It's going to take a few seconds for that app to spin up. On the serverless side, application code only executes when it's invoked, when it's basically called. So it means it's going to start faster. It also means it's only going to be billing for execution typically, so it's going to be very inexpensive. Certainly PaaS is going to reduce our operating expense versus the IaaS model, and serverless may, in certain use cases, reduce our costs even further when serverless is the right tool for the job. So just talking through serverless architecture a bit further, it's a cloud computing execution model where the cloud provider dynamically manages the allocation and the provisioning of the servers. It's hosted on a pay-as-you-go model based on use. And the resources are stateless, servers ephemeral, and often capable of being triggered. Function as a service is a great example of serverless architecture. Azure Functions, for example. Or Amazon Lambda would be the equivalent on the AWS platform. And services integration. So provisioning of multiple business services is combined with different IT services to provide a single business solution. Next up, we're going to dive into cloud deployment models. But let's start with just a quick recap of the benefits of cloud computing. It's cost effective, it's global, we have presence around the world, secure, scalable, elastic, always current. So the cloud allows us to focus as a customer on our business use cases and to hand over a lot of the care and feeding of the infrastructure and the platform to the cloud service provider. Now let's talk about the public cloud. So in the public cloud model, everything runs on your cloud provider's hardware. So the advantages here, we have the perception of infinite capacity, easy scalability, agility, a pay-as-you-go model. So we're not investing large amounts of capital in the data center, we're paying for what we use. No maintenance, low barrier to entry in terms of skills. The private cloud, on the other hand, where we're hosting 100% in our own data center, offers advantages of its own. So certainly in legacy scenarios, a dedicated environment to our infrastructure can make a lot of sense. It allows us to support legacy applications where maybe we're not ready to bring it up to a supported version for the public cloud. Maybe we need control over the environment. Maybe we have specific compliance requirements. So the private cloud enables greater control of upgrade cycles and legacy apps and support for some compliance scenarios. These are key use cases where private cloud factors prominently today. And a hybrid cloud combines public and private clouds, allowing you to run your apps in the right location. And most would say that this is the most common model today, that organizations have by and large moved at least some of their workloads into the public cloud, but they still have in large environments an on-premises data center, or at least some presence of on-premises infrastructure. So hybrid cloud, where we're connecting the private cloud to the public cloud, is very common today. And it gives us flexibility in the legacy and compliance and scalability scenarios. If we have a legacy scenario where we need control, where we have compliance concerns, we can leave that in our private data center, in our private cloud. And for apps where we don't have those hurdles, we can move those into the public cloud in the near term. But it enables the organization to control the pace of public cloud adoption. And then there's the community cloud. This is similar to private clouds in that they're not open to the general public, but they are shared by several related organizations in a community. So you could see this with an industry group, for example, that wanted to take advantage of the benefits of public cloud and perhaps take on the learnings and the risks together. And then the multi-cloud scenario. This combines resources from 2 or more public cloud service providers. This allows organizations to take advantage of service and price differences, but it can add some complexity. And we do see multi-cloud in scenarios where customers are moving to a new cloud for that price advantage, but it's easier said than done to take all of your services out of that old cloud, so we wind up in a multi-cloud scenario. So at the end of the day, Confidentiality, integrity, and availability are core objectives of security. So let's just touch on what we call the CIA triad briefly. Confidentiality, integrity, and availability. So confidentiality. Access controls to ensure that only authorized subjects can access objects. On exams, if you see subjects are generally talking about people, security principles, accessing objects. That's our data, our assets. Integrity ensures that the data or system configurations are not modified without authorization. And availability. Authorized requests for objects must be granted to subjects within a reasonable amount of time. If we don't have availability, all of our security is for naught. Now we're going to get into cloud shared considerations. So considerations in a multi-tenant environment like the cloud. The first is interoperability. So the ability of one cloud service to interact with other cloud services. That could be within a single CSP, it could be between CSPs, it could be another third party. Most of your CSPs also have a cloud marketplace with certified apps and services that provide paths for interoperability across platforms as well. Another consideration, reversibility. So this speaks to the process for cloud service customers to retrieve their data and their application artifacts, and for the CSP to delete all cloud service customer data and contractually specified cloud service derived data after an agreed period. Now, customer access to data also appears in some regulations. GDPR is one that comes immediately to mind. So let's talk about the 5 facets of cloud interoperability. The first is policy, the ability of 2 or more systems to interoperate while complying with governmental laws, regulations, and organizational mandates. The next is behavioral, where the result of the use of the exchanged information matches the expected outcome. The third is transport, the commonality of the communication between cloud consumer and provider and other providers. And this really speaks to known, standard, secure methods of transport. HTTPS, for example, or various message queuing standards. The fourth is syntactic. 2 or more systems should understand the other system's structure of exchanged information through encoding syntaxes, such as JSON and XML would be 2 good examples. And the fifth is semantic data, the ability of systems exchanging information to understand the meaning of the data model within the context. So virtual machines, containers, storage, and networking concepts. So continuing down the path of considerations, portability, the ability to move applications and associated data, as in stored within storage or database repositories, between cloud service providers, between legacy and cloud environments, or between public and private cloud environments. So think hybrid cloud, for example. And a couple of sub-considerations here. Cloud data portability, the ability to easily move data from one cloud service to another without the need to re-enter that data. We see this commonly with blob storage or with databases where we need to move a database to migrate it from one provider to another. And then cloud application portability, the ability to migrate an application from one CSP to another or between a customer's environment and a cloud service. Portability prevents vendor lock-in. So let's talk about the 3 facets of cloud data portability, and they are syntactic, so transferring data from a source system to a target system using formats that can be decoded on the target system with features like XML or open virtualization format. The second is semantic, so transferring data from a source system to a target so that the data model is understood within the context of the subject area by the target. And the third is policy, transferring data from a source system to a target so that governmental laws, regulations, and organizational mandates are followed. The fact of the matter is, if you want interoperability and you want portability, you need to pick cloud service providers that offer services that are highly standardized, that are using open and standard communication formats like XML, like JSON, like HTTPS. So continuing with shared considerations, availability. So systems and resource availability defines the success or failure of a cloud service. That's no surprise. You want to check service level SLAs and how multi-service SLAs are calculated. Your major CSPs like Microsoft, like AWS, will provide instructions in their documentation for how an SLA is calculated when you've incorporated multiple services into an integrated solution. And then resiliency, so the ability of a cloud service data center and its associated components, including your servers, storage, and so on, to continue operating in the event of a disruption. And you want to look for a cloud provider with global presence, regional redundancy, and then zone redundancy within that region. When it comes to availability, we'll talk about SLAs, OLAs, and PLAs in depth in Domain 6. So that's service level agreements, operating level agreements, and privacy level agreements. Now let's shift gears and just talk through an example. So the following example here explains these concepts in Microsoft Azure. AWS and Google Cloud Platform support the same concepts, and in fact the terminology is generally very similar, or in some cases even the same. Remember, the CCSP exam is Cloud Service Provider Agnostic, so I wanted to give you an example I had in hand to give you context. So we'll start at the global level and work our way down. So starting with an Azure geography. So this is a discrete market, typically containing 2 or more regions that preserves data residency and compliance boundaries. So with Azure, they have geographies. And you can see here, there's a geography for North America, for Europe, for Australia. China has its own geography for political reasons and legal reasons. You see Africa, you see South America. Similar concepts exist in AWS and Google Cloud Platform. And then we have regions. So this is a set of data centers deployed within a latency-defined perimeter and connected through a dedicated regional low latency network. So regions, we'd call these. So if I just look at the map here, you can see Azure includes regions all around the world. I see Japan East, UAE North, West Europe, Canada Central, Central US, West US. So regions all around the globe. And then we have region pairs. This is where it really starts to get interesting. This is a relationship between 2 Azure regions, in the Microsoft case, within the same geographic region for disaster recovery purposes. So imagine redundancy in the event of regional data center failure. So region pairs, for example, you'll find that there is a pair, a primary and a backup, chosen by the CSP, Microsoft in this case. Generally speaking, there's 300 plus miles between those 2 data centers, and your various services, like the storage platform, like the database platforms, have configurations that facilitate automatic failover of those services to the backup region. So if a region goes down, you're not dead in the water necessarily. Now, availability zones are unique physical locations within a region with independent power, network, and cooling. It's comprised of 1 or more data centers, and it's tolerant to data center failures via redundancy and isolation. So it's really focused on data center failures within a region. So my load balancer, for example, would be zone redundant across the data centers within the region. So, for example, West US for Azure is not a single data center sitting in the West US. It's several data centers, multiple data centers within that region, fairly close together, that give us these availability zones. But the focus here is data center failures within a region. But know that these concepts exist equally in AWS and Google Cloud Platform. I just wanted to give you an example in case you don't have exposure. So let's talk about security as a shared consideration. So protection of customer data, access control, data encryption, very important. Protection of cloud applications against attacks, for example, attacks of scale like distributed denial of service. Protection of cloud infrastructure, the underlying servers, storage, and network running the environment. The shared responsibility model explains who is responsible for security in each model and scenario. We talked about that earlier in this video. If you skipped over shared responsibility model, go give it a watch. Continuing down the road of shared considerations, let's talk about privacy. So data privacy in cloud computing allows collecting, storing, transferring, and sharing data over the cloud network without putting the privacy of personal data at risk. So there are a couple of prominent sources of privacy concerns. Number one, oftentimes the customer does not have knowledge about exactly how their personal information is stored and processed in the cloud. Your major CSPs do a pretty good job in terms of transparency. Those contracts, those agreements are long-winded, so not always easy to find in some cases. And then the reality that we have data breaches in recent years that have brought data privacy to the forefront as a crucial factor in cloud computing. Now, privacy versus confidentiality. I wanted to touch on the difference here. So privacy focuses on the right of an individual to have some control over how their personal information, their personally identifiable information, their protected health information is collected, used, and potentially disclosed. Confidentiality is the duty to ensure private information is kept secret to the extent that is possible. That's a legal obligation in regulatory scenarios like GDPR and a due care obligation in U.S. law. So to state all this more simply, privacy focuses on the rights of the individual person or the customer. Confidentiality focuses on the data, keeping that data confidential, private, encrypted. Next, we have performance, which is the ability of a service to remain responsive to requests of that service with an acceptable level of response latency or processing time. Remember, one of the benefits of public cloud is it delivers the perception of unlimited scale, typically for less than the cost a customer would incur to develop the same level of service in their own data center. And there's governance, enforcement of security policies and regulatory requirements, often through policy controls and regular audits. CSPs often have policy automation in which restrictions can be defined and automatically enforced throughout the service lifecycle. In fact, in Microsoft Azure, that feature is called Azure Policy that allows us to do exactly that. Next up, auditability, the ability to provide clear documentation of the actions in a data event, like a data breach or unauthorized access. And there are a couple of related activities that we need to ensure are in place in order for auditability to be true. The first is accountability, the ability to determine who caused the event. This is known sometimes as identity attribution. This requires non-repudiation, so we must have unique accounts for end users, for example, to ensure that we can pin that event back to a specific individual. And then there's traceability, the ability to track down all events related to an investigated event. Bottom line, auditability is only possible with proper logging, providing accountability and traceability. So these two things must be true for auditability to also be true. So service level agreements. These stipulate performance expectations like maximum downtimes and often include penalties, financial penalties, if the vendor doesn't meet expectations. Service level agreements are typically used with vendors. Now, operating level agreements and privacy level agreements, OLAs and PLAs, may also show up on the exam. We're going to touch on those in Domain 6. Let's talk about outsourcing for a moment. Obtaining goods or services like cloud services from an external supplier. This introduces considerations like reversibility, interoperability, and vendor lock-in, all of which we've talked about previously. It's worth noting that vendor lock-in can be a technical or a contractual constraint that prevents a customer from moving from a provider. Now we're going to move into impact of related technology. So called out explicitly in the syllabus, we see data science, machine learning, artificial intelligence, blockchain, DevSecOps, Internet of Things, containers, quantum computing, confidential computing, and edge computing. Now I'm going to throw a couple of extras related or mentioned in the official study guide just in case, and that's deep learning, fog computing, and post-quantum cryptography. Related topics I think you should be familiar with. But let's start with data science. So data science is the study of data to extract meaningful insights for business. Now, it combines principles and practices from multiple fields, mathematics, AI, computer engineering, to analyze large amounts of data. And it helps data scientists to ask and answer questions about past, current, and future events purely through evaluation of data. Now, cybersecurity data science is the practice of applying data science to prevent, detect, and remediate cybersecurity threats. Data is collected from cybersecurity sources and then analyzed to provide timely, data-driven patterns at scale. At the end of the day, the goal is to deliver more effective security insights at high scale in an automated fashion, really. So let's talk about artificial intelligence, machine learning, and deep learning. Knowing the difference can definitely help on really any security exam. So artificial intelligence focuses on accomplishing smart tasks, combining machine learning and deep learning to emulate human intelligence. And machine learning is a subset of AI using computer algorithms that improve automatically through experience and the use of data. Machine learning algorithms learn by being fed data to process and learn from. And deep learning is a subfield of machine learning concerned with algorithms inspired by the structure and function of the human brain, called artificial neural networks. And certainly in the realm of cybersecurity, data science, AI, and machine learning go hand in hand, so knowing the difference amongst these will be helpful somewhere in your career and potentially on this exam. Blockchain was originally a technology that powered Bitcoin. It does have broader uses, though. It's a distributed public ledger that can be used to store financial, medical, or other transactional data. Anyone is free to join and participate. It's a public ledger. It does not use intermediaries such as banks and financial institutions. The data is chained together with a block of data holding both the hash for that block and the hash of the preceding block. To create a new block on the chain, the computer that wishes to add the block solves a cryptographic puzzle and sends the solution to other computers participating in that blockchain. This is known as proof of work. And we have IoT, Internet of Things, which is a class of devices connected to the internet in order to provide automation, remote control, or even AI processing in a home or business setting. Due to the relevance of this topic, it's safe to guess that questions involving IoT devices are a bit more likely to appear in the 2022 exam update. Now, IoT devices suffer from some common attack vectors. One of these is default settings. Every device that you put on your network to manage has a default username and password. Often the defaults are open and available for anyone to use. And this is true of Wi-Fi and IoT devices both. Those defaults may be well known, and botnets and offensive security tools will find and exploit devices with weak default settings still in place. Just change these defaults to shut down the attack vector. That's pretty simple. In a business setting, we find that these default settings lingering generally point to a process issue. When we onboard devices to a business network, we'd expect the default settings are going to be updated to a more secure standard. We see IoT in wearables. You might be wearing an IoT device like a fitness tracker or smartwatch. They come in the form of facility automation, which would be more relevant in a business scenario. In a large facility, IoT devices are able to manage the heating and AC, lights, as well as motion, fire, and water detection. And they enable facility managers to be able to configure automation and monitoring a device function. But for critical functions like this, it's important that we shut down the low-hanging fruit that attackers are going to be looking for. And you'll even see IoT in sensors. Vehicles have very specialized sensors embedded, assisting with vehicle function often. Containerization will come up more than once in this course. We'll introduce the concept here. It's a lightweight, granular, and portable way to package applications for multiple platforms. It reduces the overhead of server virtualization by enabling containerized apps to run on a shared OS kernel. In other words, containers do not have their own OS, although the containers in the app within won't know that. They share many of the same concerns as server virtualization: isolation at the host, process, network, and storage levels. but it can be used in some cases to isolate existing applications developed to run in a VM with a dedicated operating system, just allowing us to get greater density out of our compute, because we can run more apps than we could using virtual machines. So there's a cost advantage. You'll hear about containerization in topics related to Docker and Kubernetes. So quantum computing. This is a rapidly emerging technology that harnesses the laws of quantum mechanics to solve problems too complex for classical computers. It replaces the binary 1 and 0 bits of digital computing with multi-dimensional quantum bits known as qubits. No widespread use cases as of 2023 for quantum computing, so there's very little impact outside the world of scientific research and testing. And that being said, I don't think there's a lot you could see on the exam. A quantum computer, though, could render all modern cryptography completely ineffective and require the redesign of new, stronger quantum encryption algorithms. Now this is where post-quantum cryptography can help. Let's talk a bit more and you'll understand why I bring up post-quantum cryptography in just a moment. So quantum cryptography is the practice of harnessing the principles of quantum mechanics to improve security and detect whether a third party is eavesdropping on communications. It leverages the fundamental laws of physics, such as the observer effect, which states that it is impossible to identify the location of a particle without changing that particle. Now, quantum key distribution is the most common example of quantum cryptography. By transferring data using photons of light instead of bits, a confidential key transferred between two parties cannot be copied or intercepted secretly. Now, post-quantum cryptography is something else altogether. Post-quantum cryptography refers to cryptographic algorithms, usually public key algorithms, that are thought to be secure against an attack by a quantum computer. Now, post-quantum cryptography focuses on preparing for the era of quantum computing by updating existing mathematical-based algorithms and standards. So, let's go a bit further with post-quantum. It's really the development of new kinds of cryptographic approaches that can be implemented using today's conventional computers, but that will be impervious, will be resistant to attacks from tomorrow's quantum computers. Post-quantum algorithms are sometimes called quantum-resistant cryptographic algorithms. I actually go much deeper into post-quantum cryptography in my CISSP Exam Cram. You're not going to need it for this exam, so we're not going to go there. Let's talk about edge computing. So some compute operations require processing activities to occur locally, far from the cloud, out in the field. This is common in various Internet of Things scenarios like agricultural, science and space, military, even healthcare. All the processing of data storage is closer to the sensors rather than in the cloud data center itself. With large network-connected device counts in varied locations, data encryption, spoofing protection, and authentication are all going to be important. Now, related to edge computing is fog computing. Now, while not called out in the syllabus, this is mentioned in the official study guide. So this complements cloud computing by processing data from IoT devices. Fog computing often places gateway devices in the field to collect and correlate data centrally, but at the edge. Generally, it brings cloud computing nearer to the sensor to process data closer to the device in a centralized fashion. So this is important to speed processing time and reduce dependence on cloud or internet connectivity for mission-critical situations. Healthcare is a great example of this. Next up, we have confidential computing. So the problem solved by confidential computing is that sensitive data must be encrypted in memory before an app can process it, leaving the data vulnerable. So confidential computing solves for this by isolating sensitive data in a protected CPU enclave during processing. This enclave is called a trusted execution environment, and it's secured with embedded encryption keys. And embedded attestation mechanisms ensure that the keys are accessible only to authorized application code. Next, we have DevSecOps. This is a portmanteau, a combination of development, security, and operations, DevSecOps. It integrates security as a shared responsibility throughout the entire IT lifecycle. DevSecOps really preaches that security is everyone's responsibility, and it builds a security foundation into DevOps initiatives. It appears in the CI/CD process, throughout the process, really, moving back to the left to the beginning of the process. And it often includes automating some of the security gates in the DevOps process. And in the last couple of years, we've really seen DevSecOps elevated to become kind of the de facto approach. Infrastructure as code. This is the management of cloud infrastructure, your networks, VMs, load balancers, storage, your topology described in code. And just as the same source code generates the same binary, code in the infrastructure as code model results in the same environment every time it's applied. So what I mean by that is if you had an infrastructure as code template that defined an environment with 4 virtual machines, if you applied that template and only 3 virtual machines were present, it would redeploy the 4th. If you deployed that infrastructure as code again and it saw 4 VMs were present, it would not deploy any VMs because the environment matched the template. We call that behavior idempotence. But infrastructure as code is a key DevOps practice, and it's used in conjunction with continuous integration and continuous delivery, or CI/CD, creating the CI/CD pipeline. But infrastructure as code, CI/CD, and DevOps are standard elements of deployment, change, and release in the cloud. And DevSecOps, as I mentioned, is quickly growing in popularity as well. And these 4 all go hand in hand in the same conversations. So that does it for 1.2. Moving on to section 1.3, which is understand security concepts relevant to cloud computing. We'll touch on cryptography and key management, identity and access control, data and media sanitization, network security, virtualization security, common threats, and security hygiene. And you see some specific examples called out under the headings here. We'll absolutely touch on all of those and more. So let's start with cryptography and key management. So trusted platform module. This is a chip that resides on the motherboard of a device, like a laptop, for example. It's multi-purpose, like storage and management for keys used for full disk encryption solutions like BitLocker, like dmcrypt on the Linux platform. And it provides the operating system with access to keys, but it prevents drive removal and subsequent data access. And then there's a hardware security module, commonly referred to simply as an HSM. This is a physical computing device that safeguards and manages digital keys, performs encryptions and decryption functions for digital signatures, strong authentications, and really a variety of cryptographic functions. In many ways, it's like a TPM, but these are often external devices. So let's talk about the key management strategy for the encryption key lifecycle. So encryption keys should be generated within a trusted, secure cryptographic module. FIPS 140-2 validated modules provide tamper resistance and key integrity, so that's a clear bar of high security. And then encryption keys should be distributed securely to prevent theft or compromise during transit. Best practice here, encrypt keys with a separate encryption key while distributing to other parties. And then storage. Encryption keys must be protected at rest and should never be stored in plain text. This includes keys in volatile and persistent memory, so we shouldn't have keys sitting in memory unencrypted. And then in use, so think of clients, whether those are users or their devices, they will use keys for resource access as access controls allow. Acceptable use policy sets the guardrails for data usage. So when a user is onboarded, they should sign an acceptable use policy that establishes what is and is not okay with regards to data. Revocation. We need a process for revoking access at separation in the event of a policy breach or a device or key compromise. For example, in the world of PKI, you would revoke the certificate on the issuing certificate authority. And the final phase of the life cycle is key destruction. This is the removal of an encryption key from its operational location. And key deletion goes further and removes any info that could be used to reconstruct that key. For example, in mobile device management systems, they will remove certificates from a device during device wipe or retirement. When I say mobile device management, I'm talking about solutions like Microsoft Intune or AirWatch. But regardless of how those keys are issued and how those devices are managed, there needs to be a process, an operational process for key destruction and or deletion. There are some other key management concepts we should touch on. So level of protection. So encryption keys must be secured at the same level of control or higher as the data they protect. And the sensitivity of the data is what dictates this level of protection. It's defined in the organization's data security policies. And when we're accessing that data, the system we are accessing the data from must be secured at the same level as the data as well. Key recovery. Circumstances where you need to recover a key for a particular user without that user's cooperation, like in termination or key loss. You always want to have a way to recover keys so we can get to data in those odd circumstances. Key escrow. Copies of keys held by a trusted third party in a secure environment, which can aid in many other areas of key management, including recovery. So let's talk about key management in the cloud, key management systems in particular. So all of your CSPs, Azure, AWS, Google Cloud Platform, they all offer a cloud service of some sort for centralized secure storage and access control for application secrets, a vault solution. In Azure, it's called Key Vault. AWS, it's KMS. Google Cloud Platform, it's Cloud KMS Vault. A secret in this context is anything that you want to control access to, like an API key, could be a password, certificates, tokens, cryptographic keys. And the service will typically offer programmatic access. They may have GUI access, of course, through a portal, but also programmatic access, often via an API to support DevOps and your CI/CD automation. Access control is available at the Vault instance level and to the secrets stored within the vault. So generally, control plane access and then data plane access is how I'd phrase that. And secrets and keys can generally be protected either by software or by a FIPS 140-2 Level 2 validated HSM. And whether you let the CSP manage keys in the back end or you require hardware management yourself or need to bring your own keys, that level of support is going to vary by CSP and you'll want to have those conversations directly. So let's shift gears and talk identity and access control. So in the cloud, services should include strong authentication mechanisms for validating the user's identity and their credentials, not unlike on premises. That means we need to standardize, streamline, and develop an efficient account creation process, as well as a timely deprovisioning process. So when a user departs from the company at the point of separation, we need to deprovision access quickly and efficiently. Centralized directory services, Active Directory, tends to be the most common on premises. We have Kerberos and NTLM authentication there, Kerberos being preferred. And from a privileged user management perspective, we want to manage our privileged access accounts and to enforce least privilege and need to know at all times. Separation of duties, also a good idea as an effective risk mitigation technique. We'll dive into these a bit deeper in just a moment. And then from an authentication and access management perspective, we want to focus on the manner in which users can access required resources. That means we need to design a secure authentication and authorization experience. And that's where multi-factor authentication comes into play. That's where we authenticate a user with something they know, like a PIN or a password, something they have, like a trusted device, a mobile phone with an authenticator app, for example, something you are, biometric, thumbprint, really common that we use Face ID or thumbprint on our mobile devices now. And this is going to be a prevention mechanism for multiple types of attacks. Phishing, spear phishing, keyloggers, credential stuffing, brute force, reverse brute force attacks, man in the middle. MFA can solve a lot. So let's talk about how we limit access and damage. So need to know in the principle of least privilege I mentioned are two standard security principles that are implemented in secure networks. And they limit access to data and systems so that users and other subjects have access to only what they require. That's going to help prevent security incidents. And if we have a security incident, it's going to help limit the scope of damage. So when we apply these principles, we're going to minimize the potential impact. When we ignore need to know and least privilege, we're going to expose ourselves to potentially far greater damage in the event of a security incident. So let's talk about fraud and collusion. So collusion is an agreement amongst multiple persons to perform some unauthorized or illegal actions. Separation of duties helps here, a basic principle that ensures no single person can control all the elements of a critical function. So for example, the person who configures and approves privileged access shouldn't be the person who is then using that privileged access to carry out a task. If I can grant myself God rights and do that work and then reverse those rights, if there's not a separate person in that process, that's a problem. That's a risk to the organization. And even if it's not malicious, someone might grant themselves too much permission, too much access. Job rotation is another one. If employees are rotated into different jobs or tasks are assigned to different employees, that helps with collusion for sure. But implementing these policies helps prevent fraud because it limits the actions individuals can do without colluding with others. So getting specific to cloud, let's talk about account types. So we have service accounts. In the cloud, I see those commonly called service principals, or managed identities we'll see on some platforms like Azure, for example. Now, when software is installed to run on a computer or a server, it may need privileged access to run. When we have cloud apps, they may need an identity as well, a service principal. It's a lower level administrative account, and the service account is really what fits the bill in many of these cases. A service account is really a type of administrator account used to run an application. When we get into the cloud, that service principal can be configured with the specific permissions the application needs. How that service principal is referenced will vary by platform. What they call it in Azure will be a bit different than AWS and Google Cloud Platform, but the concept certainly carries over to cloud. When we have people who perform the same duties like members of customer service, they could use a shared account. That happens. But when user-level monitoring, auditing, or non-repudiation are required, you absolutely must eliminate the use of shared accounts. Non-repudiation is how we guarantee that an action was performed by a specific person and we can prove it beyond a shadow of a doubt, so they cannot deny it. With a shared account, non-repudiation is broken. Most cloud identity providers have options to eliminate the need for shared accounts. So let's talk about privileged access management for a moment. This is a solution that helps protect privileged accounts within a tenant, preventing attacks. It also provides visibility into who is using privileged accounts and what tasks they are being used for. So native to some cloud identity providers today, you may see a just-in-time elevation feature that allows users to activate a privileged role to perform their tasks, and then that privilege is removed when they indicate they are done with the task or after a period of time, a finite period of time. Which is great because it's a more granular interpretation and application of least privilege when we have that just-in-time elevation feature that automatically removes those rights. It's definitely a process enhancement. And that's definitely true in Azure Active Directory, which is the identity provider that Microsoft gives us in the cloud. It's the identity provider with Office 365. You'll see similar capabilities with identity providers on other cloud platforms as well. Data and media sanitation may come up on the exam, and the relative security of each of the methods, so we'll cover a few here. The first is erasing, performing a delete operation against a file, files, or the media itself. Clearing, or also known as overwriting. This is preparing the media for reuse and ensuring data can't be recovered using traditional recovery tools. Now, overwriting may involve one or multiple passes, and it may use random data or zeros depending on the chosen methodology. Purging is a more intense form of clearing that prepares the media for reuse in less secure environments. Now, media is reusable with any of these methods, the media itself. Data may be recoverable with forensic tools. So in the case of overwriting, which is called out explicitly in the syllabus, so you should definitely know it, data may be recoverable depending on whether the overwriting method uses one or multiple passes with random data or zeros. Fact is, it depends. Now, more secure data destruction, crypto shredding, called out in the syllabus. Cryptographic erasure is another way to say this one. Data is encrypted with a strong encryption engine. The keys used to encrypt the data are then encrypted using a different encryption engine. Then, keys from the second round of encryption are destroyed. So the pro here is data cannot be recovered from any of the remnants on the media. The downside is this definitely involves high CPU and performance overhead. If the exam poses a question on secure data destruction, crypto shredding is almost certainly the answer. Then we have data destruction on media like hard drive or DVD or CD-ROM. These are a bit less likely to come up on the exam, but could be distractors on questions, so we'll cover them just to be thorough. Degaussing, which creates a strong magnetic field that erases data on some media and destroys electronics. We have shredding. You can shred a metal hard drive into powder. You can pulverize a drive with a hammer or drill through all the platters, rendering it inoperable. Media is not reusable with any of these methods. Data is also not recoverable by any means with any of these methods. But again, overwriting and crypto shredding are called out in the official exam syllabus and therefore the most likely to appear on the exam. Next up is network security. So we'll start with network security groups, which provide an additional layer of security for cloud resources. They act as a virtual firewall for virtual networks and the resource instances within those networks, like your VMs, your databases, and your subnets. They carry a list of security rules that include IP addresses and port ranges that will allow or deny network traffic to resource instances. But they act as a virtual firewall for a collection of cloud resources within that network with the same security posture. And how a network security group works exactly varies slightly from CSP to CSP. In Azure, for example, you can apply a network security group to a subnet or to a network adapter. But it's going to give you that IP port range filtering functionality, so it's essentially like a layer 4 firewall. Network segmentation involves restricting services that are permitted to access or be accessible from other zones using rules to control inbound and outbound traffic. Rules are enforced typically by IP address ranges of each subnet, and within a virtual network, segmentation can be used to achieve isolation. Oftentimes, we'll see network security groups used to implement port filtering. So, for example, we could put database servers in their own subnet and restrict inbound traffic just to listening database service ports. API inspection and integration. So REST APIs are the modern approach to writing web services. And this enables multi-language support, and REST can handle multiple types of calls, return different data formats. And APIs published by an organization should include encryption, authentication, rate limiting, throttling, and quotas. And in fact, in many of your CSPs, you'll find a PaaS service that allows you to publish and manage your APIs and to implement these security controls. Traffic inspection. We're really talking about packet capture here. And packet capture in the cloud generally requires specialized tools or services designed for this purpose, in that particular CSP environment, because traffic is often sent direct to resources, and promiscuous mode on a VM network adapter is not possible and maybe not effective. So what you'll find is your CSPs have a service to do this. For example, in Azure it's called Network Watcher. In AWS it's VPC traffic mirroring. But your CSPs will offer tools to facilitate packet capture within your tenant. Geofencing. So geofencing uses Global Positioning System, GPS or RFID, to establish geographic boundaries. And once a device is taken past the defined boundaries, the security team would be alerted typically. So for example, we could use geofencing to restrict access to systems and services based on where the access attempt is being generated from. We could prevent devices from being removed from the company's premises in high security situations. And we can use this to identify unusual traffic patterns and prevent misuse. Next, we're going to talk about zero trust security in the network context, but first I want to cover just a few zero trust basics. So zero trust addresses the limitations of the legacy network perimeter-based security model with a firewall and trusted and untrusted networks. It treats user identity as the control plane. It really addresses the reality that we have users that work who are much more mobile than they used to be, working from anywhere. And it assumes compromise or breach in verifying every request. Essentially, no entity is trusted by default. So let's just touch on the core 3 principles of zero trust security. The first is verify explicitly. We always authenticate and authorize based on all available data points. We're going to look at the user's identity, the location they're coming from. Are they coming from a healthy, compliant device? What service or workload are they trying to access? Are they trying to access sensitive data? Is there anything anomalous about the request? And we always use least privilege access. We limit user access. We use just-in-time and just enough access. Risk-based adaptive policies. So we're going to definitely deny authentication requests where we see, for example, impossible travel or a very unexpected location or other anomalous behavior that raises that user's risk profile. And data protection, like DLP, data loss prevention policies. And we assume breach. We're going to segment access to minimize the scope of impact. And we'll verify end-to-end encryption. We'll use analytics to get visibility and drive threat detection and improve defenses. So zero trust security in the network context means microsegmentation of our network security groups, firewalls, inbound and outbound traffic filtering, inbound and outbound traffic inspection, IDPS, looking for potentially malicious traffic, attachments, anomalous traffic patterns, and centralized security policy management and enforcement. We talked about the policy engines that our CSPs have, for example, Azure Policy. You'll also find in some cases CSPs will offer centralized policy for their firewall services, for their software-based firewalls. Containerization we touched on earlier, examples being Docker and Kubernetes. Remember, the key difference between containerization and server virtualization is containers do not have their own OS. They share a single OS kernel. And we can use containerization in some cases to isolate existing applications that were developed to run on a VM with a dedicated operating system. The container does fool the application into believing it has its own kernel, even though it doesn't. So if we look at the Type 1 bare metal hypervisor, we talked about this earlier, VMware ESXi, Microsoft Hyper-V. With virtualization, we have virtual machines with each VM in its own OS kernel and memory, resulting in more overhead. And when we look at a container host, which is generally itself a virtual machine, you'll see that the container has its binaries, its libraries, its applications, and those containers are sharing a single operating system. So they're sitting on a single host OS. That's the real difference. Each VM has its own OS kernel and memory, so the overhead is greater. Containers are isolated, but they share a single OS kernel as well as binaries and libraries where they can. And to unpack that just a bit further, the core components in a container platform like Docker or Kubernetes will include orchestration, a scheduling controller, network and storage, a container host, which is a virtual machine, container images. Think of container images as the equivalent of a VM template. A container image is to a container as a VM template is to a virtual machine. And a container registry, which is where we store our container images, and we need to secure access to that container registry. The isolation with containers is logical. We're isolating processes, compute, storage, network, secrets, and the management plane. There's a lot of isolation happening on that container host. You needn't be an expert in containerization for the exam, but you'll want to understand the concepts that we're talking about here. Now, when we look at containers in the cloud context, really what is the de facto standard today is managed Kubernetes. What you'll find is your container hosts are cloud-based virtual machines. This is where the containers run again, but your CSPs offer hosted Kubernetes services, and these handle the critical tasks for you like health monitoring and the management cluster. You basically pay for the agent nodes within your clusters. You don't pay for the management clusters. You're really paying for the container host and the compute that you're running there. Your major CSPs also offer some sort of monitoring solution that will identify at least some potential security concerns in your Kubernetes environment. And like I said, this shares many of the concerns of server virtualization, but you need to enforce isolation of network data and storage access at the container level. But really, you're going to find that managed Kubernetes is really the de facto standard that everybody is using in the world today. And your big three CSPs all have a managed Kubernetes service. In the Microsoft world, it's Azure Kubernetes Service, it's EKS on the Amazon platform, and GKE on Google Cloud Platform. So we talked about serverless technology back in section 1.2, just a couple of concerns around security related to serverless. So where possible, using an API gateway as a security buffer to protect that serverless endpoint, to avoid distributed denial of service attacks, attempts to exhaust capacity. And we want to configure secure authentication, whether that's OAuth, SAML, OpenID Connect. We might use multi-factor authentication if it's an endpoint being accessed by a person directly. We'll want to separate our development and production environments, implement least privilege. So some pretty standard security practices here, but applied in the serverless context. Now, ephemeral computing is the practice of creating a virtual computing environment as a need arises. So basically, the environment's destroyed once needs are met and resources are no longer needed. The primary use case here would be in auto-scaling scenarios where we need elasticity, rapid scale up as demands increase. And while security more or less should take care of itself in some respects, in that when you're scaling out, any security guardrails you have through security policy for the service itself should apply to the compute instances scaling out, and security should take care of itself in that when the environment's no longer needed, the resources are destroyed. You do want to make sure that when you have a service that auto scales out, that it automatically scales back in, that in fact those instances that were created are in fact destroyed and they're not sitting there dormant, but accessible. Now we're going to talk about some common threats. So the first is data breach, where sensitive data is stolen. This could include personally identifiable information or protected health information. Often due to poor application or database security design or configuration, where data is exposed without proper authorization. This is preventable by following secure development practices and adhering to recommendations in the secure data lifecycle, which we're going to touch on just a bit later in this video. And then there's data loss, when sensitive data is unknowingly exposed to the public. This is often through a system or service misconfiguration or oversharing. We'd see this commonly in the early days of cloud with Amazon S3 storage buckets that were not secured by default, exposing data unexpectedly. But a data breach is typically the result of a cyber attack. Data loss is sometimes called a data leak. It's unintentional. We have common threats to our APIs, our web services like SOAP or RESTful services. These are exposed interfaces that allow programmatic interactions between services. And they're definitely an avenue for security breach if they're not implemented properly and secured. So REST uses the HTTPS protocol for web communications to offer API endpoints. REST is the standard you're going to see most commonly today. But that API endpoint in HTTPS makes it a target for distributed denial of service attacks. Security mechanisms include API gateway, authentication, IP filtering, throttling, quotas, data validation. Most of your major CSPs offer a PaaS service that you can use to host and to secure your web services. And you'll also want to make sure that you store, distribute, and transmit your access keys for your APIs in a secure fashion. So malicious insiders. These are disgruntled employees that can wreak havoc on a system. Internal acts of disruption may include theft or sabotage, so sabotage being intentional destruction. And then there's traffic hijacking, when attacks are designed to steal or wedge themselves into the middle of a conversation in order to gain control. Abuse of cloud services. Sometimes customers misuse their cloud services for illegal or immoral activities. Insufficient due diligence, which is the process or effort to collect and analyze information before making a decision or conducting a transaction. That's due diligence. And failure to perform due diligence can result in a due care violation. Knowing the difference between due diligence and due care is actually important for your career and will be helpful in understanding what insufficient due diligence means. So let's just talk about the difference between the two briefly. So due diligence is the process of collecting and analyzing information before making a decision or conducting a transaction. Due care is doing what a reasonable person would do in a given situation. It's sometimes called the prudent person rule. So together, these will reduce senior management's culpability and downstream liability when a loss occurs, because the organization has a responsibility of due care, of implementing reasonable security to protect user data. So let's just break these down a bit further. So if we have a decision, due diligence typically happens before the decision. There's research, planning, evaluation, largely before the decision. And due care is the implementation, the operation and upkeep, the reasonable measures of security, the doing after the decision, really. So due diligence increases our understanding of the situation and therefore reduces our risk. And due care, that prudent person rule, implementing reasonable measures to reduce our liability and our exposure. But the evaluation that we perform in due diligence really helps us to determine what we need to implement as part of our due care obligation. To look at it another way, due diligence is about thinking before you act, and due care really dictates that actions speak louder than words. So you get the idea here. Another way, due diligence, do detect, and due care, do correct. That's just a little mnemonic you can use to remember the difference between the two. So hopefully that clarifies due diligence versus due care. And just to give you a couple of examples here, on the due diligence side, knowledge and research of laws and regulations, industry standards, best practices. And examples of due care would be delivery or execution, including reporting security incidents, security awareness training, disabling access at separation in a timely way. So another common threat in cloud, shared technology vulnerabilities. So the underlying infrastructure of the public cloud was not originally designed for the types of multi-tenancy we see in the public cloud. Modern virtualization software does bridge most of the gaps. Now, what threats remain in a shared public cloud infrastructure? Well, cloud infrastructure can still be vulnerable to insider threats, for sure. Unintentional misconfigurations are also a concern, and to a lesser degree, disruptive attacks of scale, denial of service, or distributed denial of service. Most of your CSPs have some layer of protection by default and additional services you can implement to reduce your DDoS exposure. Noisy neighbors can be a problem. So when you're in a multi-tenant scenario, if you have another tenant sharing a server capacity, for example, and they are noisy, meaning that they're taking up a lot of capacity, they're a heavy user, that can potentially impact you in the wrong circumstances. Less concern today. Now, for regulatory compliance and high criticality scenarios, CSPs often offer some higher isolation and flexible scale-out options. In fact, in recent years, we've seen for the highest security scenarios, you can even find some dedicated physical host scenarios available in a public cloud. So let's talk about baselining, and this really comes in the context of configuration and change management. So I'd like to tackle the bigger topic. So configuration management ensures that systems are configured similarly, configurations are known, and they are documented. So baselining ensures that systems are deployed with a common baseline or starting point, and imaging is a common baselining method. Now, change management helps reduce outages or weaken security from unauthorized changes to that baseline configuration. And versioning uses a labeling or numbering system to track changes in the updated versions of our baseline, whether that's an image, an application, or other system. And it requires changes to be requested, approved, tested, and documented. So finishing up security hygiene here at the end of section 1.3, we have patch management. This is the process of identifying, acquiring, installing, and verifying patches for products and systems. It's a function included in change management. Patches correct security and functionality problems in software and firmware. Both applicability and install are often automated with management tools. An applicability assessment is performed to determine whether a particular patch or update actually applies to a system before an attempt is made to install that patch. You'll sometimes see patch management referred to as update management. That brings us to section 1.4. Understand design principles of secure cloud computing. So here we'll touch on the cloud secure data lifecycle, cloud-based business continuity and disaster recovery planning, business impact analysis, functional security requirements, security considerations and responsibilities for different cloud categories, and finally, DevOps security. So let's start with the cloud secure data lifecycle. So the lifecycle begins with data creation. Data can be created by users. For example, a user creates a file. Data can also be created by systems. A system logs access. To ensure data is handled properly, it's important to ensure data is classified as soon as possible after creation. Ideally, data is encrypted at rest. Data should be protected by adequate security controls based on its classification, controlling its use. And when data is shared or in transit, it should be secured anytime it's in transit over the network, preferably encrypted. Archival is sometimes needed to comply with laws or regulation requiring the retention of data. And the secure data lifecycle ends with destruction. When data is no longer needed, it should be destroyed in such a way that it is not readable nor recoverable. Crypto shredding happens in this phase. So I mentioned multiple potential states of data in the secure data lifecycle. Let's just touch on these briefly. We have data in transit, which is data on the wire in flight, commonly protected with transport layer security, certificate-based security, or tunneled through a VPN. We have data at rest, in storage, on disk, in a database, protected through encryption quite typically. And we have data in use, data in memory, in RAM, CPU, or cache. It should be flushed from memory when a transaction is complete or the system is powered down, and sensitive data should always be encrypted in memory. So how can we encrypt different types of data at rest? Well, there's storage service encryption. So your CSP storage providers usually protect data at rest automatically. They usually encrypt by default before persisting it to manage disks, object file, or queue storage. We have full disk encryption, which helps you encrypt Windows or Linux ISVMs using BitLocker on the Windows platform and the DMCrypt feature of Linux to encrypt your OS and data disks. And then there's transparent data encryption. This helps protect Microsoft SQL database and data warehouses against the threat of malicious activity with real-time encryption and decryption of database backups and transaction log files at rest without requiring app changes. It's transparent and has essentially no performance impact. Some database platforms also provide row-level encryption, column-level encryption, or data masking. On the topic of data security, you may see questions regarding data roles on the exam. So 2 roles you should definitely know for the exam. Data owner, who holds the legal rights and complete control over a single piece of data. Usually a member of senior management. They can delegate some day-to-day duties. They cannot, though, delegate their total responsibility for that data. And then there's the data custodian, who's responsible for safe custody, transport, and storage of data, implementation of business rules, technical controls, confidentiality, integrity, and availability, audit trails. Usually someone in the IT department. They don't decide what controls are needed, but they do implement those controls for the data owner. Tip here, if the question mentions day-to-day responsibility, that's the custodian. So there are a couple of GDPR data roles that are worth knowing just in case for the exam. That's the data processor, a natural or legal person, public authority, agency, or other body that processes personal data solely on behalf of the data controller. The data controller is the person or entity that controls processing of the data. These are in the official study guide, so they may well appear on the exam. And other data roles. There's the data subject, and I've mentioned this briefly earlier in the course. This refers to any individual person who can be identified directly or indirectly via an identifier, the subject, I called them. Identifiers may include name, an ID number, location data, or via factors specific to the person's physical, psychological, genetic, mental, economic, cultural, or social identity. Any way we can identify that person. And then the data steward, who ensures the data's context and meaning are understood and business rules governing the data's usage are in place. They use that knowledge to ensure the data they're responsible for is used as intended. So let's talk about business continuity and disaster recovery. A couple of definitions related to business continuity and disaster recovery worth knowing. So we have the business continuity plan, which is the overall organizational plan for how to continue business. And then the disaster recovery plan, which is the plan for recovering from a disaster, impacting IT, and returning the IT infrastructure to operation. So what's the difference between business continuity planning and disaster recovery planning? Well, business continuity planning focuses on the whole business, where disaster recovery planning focuses more on the technical aspects of recovery. Business continuity planning will cover communications and process more broadly. Basically, business continuity planning is an umbrella policy, and disaster recovery planning is part of it. Disaster recovery is built into cloud architecture, and there are some concepts we covered earlier that come into play here. Region pairs address site-level failure, so we could lose an entire region, like West US, for example. And region pairs are 300 plus miles apart. They're selected by the CSP to ensure that a disaster doesn't impact both the primary and the backup Availability zones address data center failures within a cloud region. So remember, within a region like East US or West US, you have multiple data centers in fairly close proximity. A CSP region like East US would include multiple data centers, not just a single regional data center. And availability sets address rack level failures within the data center itself. So this consists of 2 or more fault domains for power or network, etc. You may see questions around business impact analysis on the exam. And a business impact analysis contains 2 important items: a cost-benefit analysis and a calculation of the return on investment. Now, a cost-benefit analysis lists the benefits of the decision alongside their corresponding cost. And it can stop there. A cost-benefit analysis can be strictly quantitative, just adding the financial benefits and subtracting the associated costs to determine whether a decision will be profitable. A thorough cost-benefit analysis will consider intangible benefits, those that you cannot calculate directly. Functional security requirements. So what's the difference between functional and non-functional security? Well, functional security requirements define a system or its component and specifies what it must do. It's captured in use cases, it's defined at a component level. For example, application forms must protect against injection attacks. We do this by writing input validation into our application forms. It specifies a specific function. Non-functional security requirements, on the other hand, specify the system's quality, characteristics, or attributes. They apply to the whole system, the system level. For example, security certifications are non-functional. If we say a system must be FedRAMP certified or ISO 27001 or HIPAA certified. Security considerations for different cloud categories. We'll touch on IaaS, PaaS, and SaaS, the 3 core categories of cloud computing. So in the IaaS space, where we're thinking about server virtualization, we have VM attacks, our virtual network, hypervisor attacks, VM-based rootkits, virtual switch attacks, colocation, denial of service. On the PaaS side, we have system and resource isolation, user-level permissions, access management, protection against malware, backdoors, and Trojans. And in SaaS, we have data segregation, data access and policies, and web application security. Notice here, as we move from IaaS to PaaS to SaaS, the list of considerations gets shorter. And if you remember back to the shared responsibility model, the customer has the most responsibility in the IaaS category, and the cloud service provider takes on more and more responsibility as we move to the right. So your considerations are fewer as we move from left to right on this page. The attack surface, shared responsibility, and data sensitivity all influence attack and defense strategies. But if you go back to the shared responsibility model, it makes sense why we see fewer concerns as we move from left to right on this chart. So virtualization-focused attacks. There's VM escape, where an attacker gains access to a VM, then attacks either the host machine that holds all the VMs, the hypervisor, or even some of the other VMs. Protection from VM escape, we ensure patches and hypervisor and VMs are always up to date, guest privileges are low, and server-level redundancy, intrusion prevention, and detection are also in place and in effect. There's VM sprawl, when unmanaged VMs have been deployed onto your network, and because IT doesn't know it's there, it may not be patched and protected, and thus it's more vulnerable to attack. So to avoid VM sprawl, enforcement of security policies for adding VMs to the network, as well as periodic scanning to identify new virtualization hosts on our network. And these would apply to both VMs and VM container hosts that we use in containerization, like Docker and Kubernetes. Application attacks. So these are attacks attackers use to exploit poorly written software. We have rootkit, which is escalation of privilege. These are freely available on the internet, and they exploit known vulnerabilities in various operating systems, enabling attackers to elevate privilege on a system. And we can stop most rootkit-based threats by simply keeping security patches up to date. Anti-malware software is good. EDR, XDR solutions installed on our host to watch for malicious activity. Backdoor attacks, these are undocumented command sequences that allow individuals with knowledge of the backdoor to bypass normal access restrictions. These are often used in development and debugging operations, a backdoor for the developer. Countermeasures here would be firewalls, anti-malware, network monitoring, and code review to catch these backdoors before they make it into production. We want to make sure that backdoors don't exist, generally speaking. Network attacks. There's denial of service, which is a resource consumption attack intended to prevent legitimate activity on a victimized system. And then there's distributed denial of service, DDoS, which is a denial of service attack utilizing multiple compromised computer systems as sources of attack. Countermeasures are firewalls, routers, intrusion detection, a SIM solution, disabling broadcast packets entering and leaving our network, disabling echo replies, patching. DOS attacks are really a class of attacks. There are many different types of denial of service and distributed denial of service attacks, so we consider these a class of attacks. So types of distributed denial of service. You have network-based attacks, which are targeting flaws in network protocols. They often use botnets, techniques like UDP, ICMP, flooding, SYN flooding. Application attacks. So exploit weaknesses in the application layer, the layer 7, by opening connections and initiating process and transaction requests that consume the finite resources like disk space and available memory. We have operational technology, or OT, DDoS attacks. These target weaknesses of software and hardware devices that control systems in factories, power plants, and other industries like IoT devices. They often target weaknesses using network and application techniques that we described above here in the other two. There are a few effective countermeasures to DDoS attacks. Intrusion detection and prevention, rate limiting, limiting the number of requests that can come to a system in a given period of time, firewall egress and ingress filters. And your cloud service providers will generally have DDoS protections built into their platform. So there's really an invisible layer of protection that's there by default, and they even in some cases have a premium SKU of DDoS protection you can buy that has additional levels of configurability for your cloud services and your environment. And wrapping up section 1.4, we have DevOps security. So DevOps relies heavily on deployment automation to deliver continuous integration and continuous delivery, that CI/CD automation we talked about earlier. And security controls should be implemented to mitigate risks. So you have two categories of security controls. You have technical controls, like automated software scanning, vulnerability scanning, web application firewalls, software dependency management, access and activity logging, and application performance management. And then we have administrative controls, like developer application security training, documented policies and procedures, code review, approval gates in our CI/CD process. And that brings us to section 1.5, evaluate cloud service providers. In fact, section 1.5 is the last in domain 1, so we'll finish up with a look at verification against criteria. And we'll touch on ISO IEC 27017 as well as the Payment Card Industry Data Security Standard, or PCI DSS. And we'll talk about system product certifications. We'll have a look at common criteria as well as the Federal Information Processing Standard, or FIPS 140-2. So let's start with ISO IEC 27017. So this provides guidelines for information security controls applicable to the provision and use of cloud services. It provides cloud-based guidance on several ISO IEC 27002 controls, along with 7 cloud controls that address who is responsible for what between the cloud service provider and the cloud customer, the removal and return of assets when a contract is terminated, protection and separation of the customer's virtual environment, virtual machine configuration, administrative operations and procedures associated with the cloud environment, customer monitoring of activity within the cloud, and virtual and cloud network environment alignment. PCI DSS stands for Payment Card Industry Data Security Standard. It's a widely accepted set of policies and procedures intended to optimize the security of credit, debit, and cash card transactions. And it's not a government-enforced regulation at all. It was actually created jointly in 2004 by 4 major credit card companies, Visa, MasterCard, Discover, and American Express, and it's enforced contractually between these card companies and their vendors, their merchants. So it's based on 6 major objectives. A secure network must be maintained in which transactions will be conducted. Cardholder information must be protected wherever it's stored. Systems should be protected against the activities of malicious hackers. Cardholder data should be protected physically as well as electronically. And networks must be constantly monitored and regularly tested. And finally, a formal information security policy must be defined, maintained, and followed. Next up, we have ISO IEC 15408 Common Criteria, which enables an objective evaluation to validate that a particular product or system satisfies a defined set of security requirements. It ensures customers that security products they purchase have been thoroughly tested by independent third-party testers and meets customer requirements. The certification of the product only certifies product capabilities. If it's misconfigured or mismanaged, software is no more secure than anything else the customer might use. It's designed to provide assurances for security claims by vendors. And in fact, common criteria is used almost exclusively by government agencies. Let's talk about FIPS 140-2. That's Federal Information Processing Standard. It was established to aid in the protection of digitally stored, unclassified, yet sensitive information. It was developed by the National Institute of Standards and Technology, NIST, for use in computer systems by non-military American government agencies and government contractors. So there are 3 FIPS security levels you want to be familiar with. There's level 1, which is the lowest level of security. There's level 2 that specifies the security requirements for cryptographic modules that protect sensitive information, and level 3 that requires physical protections to ensure a high degree of confidence that any attempts to tamper are evident and detectable. And as we close out Domain 1, I want to point you to some useful documentation from CSPs and industry groups with guidance on cloud design and security. So in the architecture category, we have the AWS Well-Architected Framework, the Azure Well-Architected Framework, and the Google Cloud Architecture Framework. From industry groups, we have Enterprise Architecture Reference Guide from the Cloud Security Alliance, the Cloud Computing Reference Architecture from NIST, and these really obviously focus on architecture more than security, but there's going to be some security content in there. Now, security focused, we have the Microsoft Cybersecurity Reference Architecture, the AWS Security Reference Architecture, and the Google Cloud Security Foundations Guide. Now, from the industry, we have the Enterprise Cloud Security Architecture from SANS, the Security Technical Reference Architecture from CISA, and the Cloud Computing Security Reference Architecture from NIST. Skimming the SANS, CISA, and NIST docs may be helpful for the exam, purely optional if you're curious. But congratulations, you've made it to the end of Domain 1. I hope you're getting value out of the series. I'll look forward to seeing you over the next several weeks back for installments 2 through 6. Feel free to reach out anytime with questions in the comments below these videos here on YouTube. And until next time, take care and stay safe.